Everyone, my name's Christina,
And I'm Mike.
and we are going to discuss our heliotropic solar panel mechanism.
Starting with our design specifications, we chose a mounting style of equatorial, which will allow us to track the sun from east to west. A different angle will be required for each season, which will be a manual input. Winter requires 24 degree from the vertical, fall and spring a 47 degree, and summer a 70 degree. The mechanism can only be 1 degree of freedom and driven by a rotary motor with no computer tracking. We decided that the mechanism must fit within a 25-foot cubed volume and have a time ratio of 1.4 to 1. The mechanism was designed using both sketching techniques as well as the GeoGebra program. We used the time ratio so that the solar panel can follow the sun from sunrise to sunset. Now this allowed for a 150-degree rotation of the solar panel so that it could track the sun during the day and return at night.
This mechanism was designed to have two toggle positions, one at its initial position at 0 degrees and the second at its final position at 150 degrees. It's important to note that it reaches this final position after 13 hours and returns to its initial in 11 hours. It's important to note that these two toggle positions have transmission angles corresponding to them. For our initial toggle position, we have a transmission angle at 39 degrees, and for our final toggle position, we have a transmission angle at 15 degrees. Looking at our solar panel angle versus our crank angle, we see that our first section here, as it's reaching its final position, is linear, while it's returning, it is exponential. This is because it's traveling the same distance in a shorter amount of time. Another thing to notice here is that we do reach our specified angular displacement of 150 degrees as it goes from a negative 110 all the way up to 40 in this graph. So in order to achieve these in real life, we need to have a motor speed that is equal to 6.944 times 10 to the negative fourth revolutions per minute.
Here we can see the solar panel going through its 24 degree, 47 degree, and 70 degree angles for the different seasons. In real application, one would stick a bolt through the holes to get it to lock at that orientation. Here we can see an animation of the solar panel and the mechanism going through its motions. It's starting at its 0 degree and it's making its way to its 150, where then we'll see it turn around and come back faster than it got there. Enjoy!
First, looking at the success of our project, we did meet a lot of the design specifications set out. The first being that the solar panel does in fact have an angular displacement of 150 degrees to properly track the sun from east to west. Furthermore, we have a final volume of around 19 feet cubed, which was in our desired bounds of 25 feet cubed. We can also, as seen before, adjust to our seasonal angles, and our primary design specification of having 1 degree of freedom mechanism driven by a rotary motor was met. Looking at our future improvements, our design specification called for a 1.4 to 1 time ratio, but we achieved 1.2. It's still adequate for our purpose, but if we were to have more time with this project, we would make sure to get that time ratio there. Thank you.